So continuing on from my last video is we're basically just gonna continue doing some integrals. I'm just gonna throw a whole bunch of integrals at us and we'll just see how we do. Really only one new principle I have to cover, and that's gonna make this video a little shorter. In the last video, I spent the first like 6-7 minutes covering, just the basic properties of integrals. There's really only one I need to talk about in this one, and that's just, it's the integral of, it's an indefinite integral, right? It's an indefinite integral like I established last video. And if you do that, remember that if it was a definite integral, like from a to b, f of x dx, I got, big F a minus big F b, or sorry, big F b minus big F a. And I got some number, right? We always got some number or some value, or, some things that didn't even look like a value, right? They would be like natural log of something, and they can look pretty ugly. But what you really have to know is that, if you take a definite integral, you're going to get some number. If you take an indefinite integral, you're going to get the antiderivative plus some value c. Again, this goes back to my antiderivatives video. It's the same exact thing. We're just doing the antiderivative, and then we're tacking on a plus c value. And I go over the reasoning behind adding that plus c over in my antiderivatives video if you want to check that out. So it's really the only topic here. I'm only bringing this up is because as we do some of these integrals, the first couple are indefinite integrals. So I'm just going to clear the board now and we'll just get started. We're just going to do a whole ton of integral examples. And hopefully after this video, you'll feel a lot more comfortable with integrals in general. And again, if you want to know some real key techniques in studying for integrals, just do a bunch of them. Honestly, just do a bunch of them. Do as many as you can. Okay, so let's say I had the integral of 5 plus 2/3 x squared plus 3/4 x cubed with respect to x. Okay, so this is an indefinite integral, right? So I'm not going to get a value. I'm not going to get like, pi or pi squared over 4 or something like that, or 5 or 10. I'm going to get an expression. I'm going to get an expression like some function, and then I tack on a c value, so plus c. Okay, so we can break this up. We can take the integral of this and that and that. So again, because, integrals work between addition and subtraction. So the integral of 5, well, that just becomes a 5x, right? So plus 2/3 x squared, well, that's 2/3 x squared, and then, or sorry, 2/3 x cubed. We add 1 to the exponent, and then we divide by 3, plus 3/4 x to the 4th, and then we divide by 4, right? And then we add on that c value. Okay, and then now I'm just going to clean this up a little bit. This is going to become 2/9 x cubed plus 3/16 x to the 4th plus c. And from now on in this video, I'm not really going to write it like this. I'm not going to do 2/3 x cubed divided by 3 or 3/4 x 4th divided by 4. I'm just going to kind of go from here to here. Reason being is as you do these integrals, you're not going to have to write this anymore. You'll literally just say in your head, this becomes an x cubed, and you'll say 2/3 divided by 3, and you can just plug that in your calculator or do it in your head, and then you'll just arrive straight at this answer. I just divided by 3 to kind of refresh your memory on what's happening. You add 1 to the exponent, and then you divide the whole thing by the new exponent. So this is our answer, right? This is an indefinite integral, definitely. It's an expression, and then we add on a c value. So that's our first example. And I'll just write number 1 right here. So now let's do another one. So let's say I had sine 2x over sine x. Okay, well, is there anything I can even do? Like, I can't split this up into addition and subtraction. I can't, there's nothing really I can do. And you might just look at this and be like, well, I'm stuck, right? There is no product rule, there is no quotient rule, there is no chain rule. So what we can do, though, is we can use some good old trig identities to basically bail us out of this one. So recall that sine 2x is the same thing as 2 sine x cosine x, or 2 cosine x sine x, doesn't matter. It's multiplication, so the order does not matter. So I'm going to use this property right here to help me get out of this integral. So 2 sine x cosine x all over sine x. Okay? Now what's going to happen is that these two sine x's will cancel out. Okay? And then I'll be left with 2 cosine x dx. And then we just take the integral of that. You know, the integral of cosine is just sine. So 2 sine x, and then don't forget your plus c value. So plus c. And that's it. So, you know, sometimes, you know, it's not really just going to be straightforward addition and subtraction. Sometimes you're going to have to do some algebraic manipulations or trigonometric identities to help get you out of the integral. There were a few in my antiderivatives video that covered this. So if you want, you know, go check that one out. Sorry for my shameless self-promo on that video. I just feel like it really helps. So there's that, right? So this case, you know, we saw this wasn't addition and subtraction, so then we thought, hey, are there any trig identities we can use to get out of this? There was. Sine 2x became 2 sine x cosine x. These canceled, right? And then I was left with 2 cosine x, and I said, hey, that's something I can integrate. So then I did that, and I got 2 sine x plus c. So there's that one. Okay, moving along here to example number 3. We're kind of just tearing right through these, so that's pretty good. So let's say I had 0 to 1. So now we're working with definite integrals. So I know my answer is going to be some value or some number. So x times cube root of x plus the fourth root of x. And this looks scarier than it really is, but let's just see what we can do with it. Okay, so it's running from 0 to 1. And what I want to do is whenever you see, you know, roots, you know, square roots, cube roots, fourth roots, always write them as powers. So x, the cube root of x, that's the same thing as x to the 1/3. Fourth root of x, that's the same thing as x to the 1/4. Okay, and now what I want to do is I just want to distribute this x in. I'm going to distribute it over here and over here. So number properties of exponents, you add the exponents together. There's an invisible 1 on this x, so that becomes x to the 1 plus 1/3, 4/3, 1 plus 1/4, 5/4. Okay, and that's it. So now let's take the integral of this. Okay, well, integral of 4/3, the integral of 4/3, well, that's just going to become, well, what's 4/3 plus 1? 7/3. So then if you divide 1 by that, it's just going to become 3/7, so 3/7. And now let me just do that one more time because it just looks a little confusing. So 4/3 plus 1 is 7/3. Okay, and then you divide by 7/3. But dividing is the same thing as multiplying by its reciprocal. It's the same thing as if I were to say, hey, this is the same thing as multiplication by 3/7. Okay. Okay, and then what's 5/4 plus 1? That's going to be 9/4, so x to the 9/4. And then we divide by 9/4, but division of 9/4 is the same thing as multiplication by this one's reciprocal. So it's the same thing as multiplying by 4/9. So 4/9 x to the 9/4. And we draw the bar. And this is still running from 0 to 1. We haven't changed limits of integration. They stay like that. Okay, so now remember we plug the 1 in. We plug the 1 into our integral. So 1 7/3 plus 4/9 times 1 to the 9/4. And then minus, always a subtraction sign. And then we plug in the 0. So minus 3/7 times 0. 7/3 plus 4/9 times 0 to the 9/4. Okay, so this is just going to be 3/7 plus 4/9 minus 0 plus 0. And 3/7 plus 4/9, that happens to be 55 over 63. And that's the end for that one. You know, pretty simple. Again, this one was just a little more complicated and a little more tedious because I was dealing with some fractions in it. So that's pretty much it for that one. So now let's do one more example. Let's just do one more, and then I'll make one last video on a couple more extra integrals. Okay, so we're just gonna clear all this away. So just gonna clear the board right now. Okay, so let's do this one. So this is example number 4, I believe. So this one's gonna run from pi over 6 to pi over 2. And this is theta plus 2 over sine squared theta, and then d theta. Again, these parentheses out there don't matter. You can leave them if you want. It doesn't matter. Okay, well, let's try to deal with this. Well, theta I can integrate just fine, but 2 over sine squared theta, it's not really something I can just integrate. There's no possible way to do that. Well, there is, but there's not an easy way. But what I can do is I can use some trig identities to manipulate this. I can always do a trig manipulation or an algebraic manipulation. So what if I rewrote it like this? Theta plus 2 times 1 over sine squared theta. Now it's coming together just a little bit. So just bear with me here and we'll see if we can fix this. Well, 1 over sine squared, remember 1 over sine, that's the same thing as cosecant, right? 1 over sine squared, that's the same thing as cosecant squared. So what's going to happen is that 1 over sine squared, that's the same thing as cosecant squared. So, and I'll get rid of these parentheses too, just to kind of show that we don't need them. So plus 2 cosecant squared d theta. And remember, cosecant squared is something we can integrate, right? That's definitely something we can integrate. So the integral of cosecant squared, that's just negative cotangent, right? Because think about it, if I differentiated cotangent, that just gives me negative cosecant squared. So that was cotangent x. But there's a negative out here, but I get a positive cosecant, right? You see, I get a positive cosecant as my result. Hence, I would have to differentiate negative cotangent x to get just a positive cosecant squared. That's the reason. So now what's going to happen is that basically, 2 cosecant squared, that's going to integrate to negative 2 cotangent. And this theta, just pretend it's an x. It's just theta, the 1, you add 1 to the exponent, and you divide by 2. That's the same thing as 1/2 theta squared. Okay, so 1/2 theta squared plus, so I'll just say, so plus negative 2 cotangent theta, and this is running from pi over 2 to pi over 6. Okay. So now we just plug in, right? We plug in our upper limit of integration, so 1/2 times pi over 2 squared minus, and this is a plus a negative, so I'm just going to write minus. Hope that's okay. It's minus 2 cotangent pi over 2, and then a minus sign because we're done plugging in the upper limit of integration. Now we're going to plug in the lower one. So 1/2 pi over 6 squared minus 2 cotangent of pi over 6. So now let's clean this up. So pi over 2 squared, well, that's the same thing as pi squared over 4. And then minus 0, right? 2 cotangent pi over 2, cotangent pi over 2 is just 0. Okay? And then 1/2, well, that's pi squared over 36, just squaring pi over 6, minus 2 cotangent pi over 6, well, pi over 6, cotangent of it, that's just minus 2 rad 3. Okay? And now I'm just going to multiply these two together and just combine like terms. So pi squared over 8 minus pi squared over 72. And then you see, like, this negative right here, it's distributing. So I got a minus 1/2 pi squared over 36, and then minus a negative 2/3, so that'll just become a positive 2/3. And then if I want to, you can leave it like this, but if you want to simplify it even more, you could just say pi squared over 9 plus 2 rad 3. And that's your answer right there. So pretty messy answer. Sometimes these integrals can have really clean answers, you know, like 1 or something, or 5. Other times they can have pretty messy results. So that's really it for this one. And let's actually just go on to the next ones. You know, I didn't want to make this video too long, but I only have 2 more examples. So let's just get through them. This video might be a little longer than I wanted, but it's okay. So let's just move on to the next one. So my next example is, let's say I had the integral from 0 to 1 of 5x minus 5 to the x dx. So one thing I want to point out is that the integral of 5 to the x dx is equal to 5 to the x over ln of 5. That's just a general rule for integrals. You know, if it's b to the x, it's simply just b to the x over ln of b. Pretty similar to the derivative one, except instead of 5 to the x times ln of 5 or something, or b to the x times ln of b, it's divided by ln of b. So no big deal. Okay, so let's integrate this. So we add 1 to the exponent, that becomes 2, and then we divide by it. So 5 halves x squared minus 5 to the x over ln of 5. We draw this bar because it's a definite integral. And then now we plug in. So 5 halves 1 squared minus 5 to the 1 over ln of 5 minus, always the minus. Now we plug in the 0, so 5 halves 0 squared minus 5 to the 0 over ln of 5. So now we're getting somewhere. So I'm going to have 5 halves minus 5 over ln of 5, because 5 to the first is just 5. This would just become a 0 because it's being multiplied by 0. And you see I'm subtracting a negative. See, this negative gets distributed over here. So negative, negative, that's a positive. And this is 5 to the 0. Remember that anything to the 0 power is just 1. So 5 to the 0 is just 1 over ln of 5. And I'm going to get 5 halves. I have a negative 5 over ln of 5 and a 1 over ln of 5. So that's going to be minus 4 over ln of 5. And that's my answer right there. So pretty easy. You know, I only did that one because I wanted you to remember the rule for, you know, integrating where x is the power. That's all. Okay, so last one. I'm just going to clear the board and we'll get this one settled. We'll get this whole video settled. Okay, so this is probably the weirdest one of all. I definitely get asked this one a lot, so just bear with me on this. So 0, 3, and then we do the absolute value of x squared minus 4. Okay, so absolute value is a weird thing because there is no rule for integrating absolute values. But when you see an absolute value, what you have to do is you have to take this part, the part that's in the absolute value, and you have to see where is it positive and where is it negative. So I'm going to do x squared minus 4 equals 0, right? So let me just rewrite that. Minus 4 equals 0. And I'm just going to find out the 0 values. So x minus 2, x plus 2 equals 0. X is equal to 2. X is equal to negative 2. And I just kind of draw this number line with negative 2 and 2 as my check marks. Again, you might have other ways of seeing this. This really goes back to earlier in calculus, you know, when you're finding max and mins, and you have to see like, hey, where is it increasing, where is it decreasing? Kind of something similar, except we're not working with derivatives. So I'm going to look at x squared minus 4. Okay. So where is it increasing? Where is it decreasing? So I'm going to plug in some value to the left of negative 2. Let's just try negative 100. that would definitely be positive because negative 100 squared, that's some really big number. Positive number, minus 4. Okay, now we'll plug in like 0. 0 squared minus 4, that's going to be a negative. And then let's plug in a big number like 10. 10 squared minus 4, 100 minus 4, 96, it's positive. Okay. And again, if I did this pretty fast, I encourage you to refresh yourself on determining when a function is positive, negative, or increasing, decreasing, and so on and so forth. But keep in mind one thing. This integral runs from 0 to 3. It runs from 0 to 3. So those are the only two, those are the bounds I care about. I don't really care about all this stuff, but I just put them for just to make this complete. So runs from 0 to 3. That's all I care about. So what I do now is I break this up. And where it's negative, I put a negative in front of it. So it's negative from 0 to where? 0 to 2. So 0 to 2. And then I say negative x squared minus 4. Okay? And then you do plus. And then where is it positive? From 2 to 3. And again, it's positive from 2 onwards technically, but our integral only runs from 0 to 3. So I'm just going to say 2 to 3. And there's a positive in front of it, so I just simply say x squared minus 4. Oh, and then that's really all there is to it. You look at where this function is negative, it's from 0 to 2, so I did that, and I just put a negative out front of this. And then I looked at where it was positive, and then I didn't touch it, and you just have to adjust your limits of integration accordingly. So now let's distribute this negative in here, and we just have to do two definite integrals now. So 0 to negative x squared plus 4 plus 2, 3 x squared minus 4. I'm sorry, I forgot my dx's. Okay. And then now we just take the definite integral. So negative 1/3 x cubed plus 4x times 2, start from 2 to 0, plus, well, 1/3, and I'll write parentheses around this so it's a little easier to see. 1/3 x cubed minus 4x from 2 to 3. Okay, and then I just have to plug all of this stuff in. So negative 1/3. So negative 1/3 times 2 cubed plus 4 times 2. And let me just kind of do this right now. Minus negative 1/3 times 0 cubed plus 4 times 0. Okay. Now what I have to do is plug it enough over here too. So 1/3 3 cubed minus 4 times 3. And then we do a minus. So we do the minus sign, then we plug in 2. So 1/3 2 cubed minus 4 times 2. And from here, it's really just plug and chug. I don't really want to add all of these together on the spot right now. That would make this video insanely long, already longer than it needs to be. So if you compute all of this, if you plug all these values into the calculator, you get 23/3. And, I didn't do it in front of you guys right here because I felt like, this video is for integration. It's not, watch me do basic arithmetic for 20 minutes straight while you sit there and kind of just wait for me to get the answer. So that's the answer, and I trust you guys will be able to do all of this arithmetic up here. Again, I probably could have done it pretty quickly, but I didn't want to waste time. So that's really all there is for integrals. And in the next video, I'll be talking about U substitution, which is another method for evaluating integrals. So hope this helps. I hope you learned about what an indefinite integral is, what a definite integral is, and how to evaluate them accordingly. So as always, if you have any questions on topics you want me to cover, feel free to message me. And as always, thanks for watching.